All right, well, so a lot of folks struggle that there is always noise or randomness in our data. Uh, Stochastic data is everything that we have. There's always some randomness in it. Einstein struggled with the idea that the universe had inherent randomness in it. We now know that it does, or at least scientists believe that it does, based on huge amounts of research, even that at the subatomic level. There are normal distributions for how you find the locations of subatomic particles. So it looks like randomness or noise is built into our universe. What's left over then is we can't be deterministic anymore. It's very rare that we'll have something that's deterministic unless it's something we've made up. What is left is quantifiable probability with uncertainty. So it's not a disaster. It's simply that we change our expectations to say we can't find the exact answer, but we can say, hey, 90% of the time, this is going to work. Okay, now we can also say there's 10% the time it's not going to work. So we can get more and more rigorous with predicting when things will work and when they won't, what the chance is. And that's all we've got. I'm okay with that. All right, so again, all data includes some uncertainty. Unfortunately, it's usually not documented. So when you get your field data and your covariates, quite often you'll just get them and there won't be any data associated with them. Sometimes the uncertainty information will be there, especially for folks like NOAA and NASA. You can track it down on their websites. It's often hard to get. And then most modeling methods don't provide uncertainty outputs. So some of them do, but some of them, most of them don't. As you've seen with the methods we've used so far, none of them output like any kind of error information for the model. They talk about how much deviance they explain, but not the amount of error inherent. And that's partly because they don't know about the error that's inherent in your sample data and in your covariates. We need to provide that information to them. So what can we do? Basically use Monte Carlo method. That's what I've been talking about. We can estimate the uncertainty in the measured values in the predictor variables or covariates. Then we use Monte Carlo methods. We inject noise into the data. We create the model. We do that over and over again, measuring the impact that the noise has on the model. And then find the distribution of the model outputs. And that can be your performance characteristics. It can be the model estimated parameters. It can also be your actual maps and predicted surfaces. So, and this is, by the way, cutting edge stuff. It's done now. It wasn't done when I got started in modeling. I was one of the first people to start actually doing this and publishing on it. And now it's fairly common. But I think it needs to be done more because it tells us how good our models are. All right, so if we follow our path here through doing a model in R, what we do is we inject noise, and we can inject noise into our covariate values before we create the model. We can also inject them into our XY coordinates, okay, so that when we extract our values, they're going to change a little bit. This would be simulating the error of our GPS or however we found our coordinates. And that, of course, we can quantify based on the method that was used. Mean temp, max temp, there is data on BioClimb and the PRISM sites about the nature of the error in these layers. Please see Melissa Kimball's thesis for information on that. It's a little bit easier to get to the information in there. And then we create the model from that. And now we've also got our layer that we're going to use to create our surface. If that is a separate layer, we can then inject noise into those covariate values as well, and then convert that to a raster. So in these two areas, we're simulating the noise that's inherent in our covariates, our locations, and if you have other measured variables like height of the tree, you can inject some noise in there as well. And we do an R script that does this over and over and over again, all by itself. You just leave it to run, and it pumps out information on the results. Okay, so again, field data with the XY values, the measurements, and then our predicted layers. The ones that are interpolated are going to have the highest level of uncertainty, certainly that I've seen. So this is, again, especially the ones interpolated from the weather stations. And the remotely sensed data is going to have much lower level of uncertainty, but still some uncertainty in them. One of the places we can really get a handle around what's happening with our data is when we look at downsampling. So here I've taken a DEM from around Humboldt Bay, and I've gone ahead and downsampled it pretty heavily. It's probably a 10-meter DEM, and I've downsampled it a lot. So you can see right away we've lost a lot of information. But what is really happening with these pixels, right? What do these pixels really represent? Well, here's a section of the original DEM, and then here's the one at 90 meters. So this is 10 meters. This is 90 meters. So I've downsampled it by a factor of 9 in each direction. So realize that means for every 1 pixel here, okay, it's 9 by 9. So it's 81 pixels in this original image. Now, when you downsample, if you pick the mean value, which what most people do, what you're really getting is a raster of the mean pixel value from the pixels values that were inside this pixel. Okay, so we're really not getting elevation, we're getting the mean of the elevation of the pixels within this pixel. Okay, so you can start to think of each pixel as being a little probability distribution in and of itself, and this is the mean. What we're missing is the standard deviation. Well, of course, when we do the downsample, we can get the standard deviation. Now, again, not all software outputs this, but we can do it even in R when we downsample. We can get a standard deviation. You can see that up here where things are relatively flat, the standard deviation, here where they're relatively flat, the standard deviation of these pixels is pretty small as compared to where we have these canyons and these steep slopes here. Standard deviation is going to be much higher, these lighter areas. So now we have the mean and the standard deviation of the pixels that were downsampled. I think it's kind of cool. Okay, now if you're looking at remote sense layers, other remote sense layers, there's an excellent paper called What's in a Pixel by Cracknell that talks about how, yes, cows are not 30 meters on a side, nor are rivers and trees and houses and other things that we see. So in other words, whenever you have a remotely sensed layer, it's the same thing. It's got some statistical distribution of how it sampled the data that was inside of the pixel that it represents. And Cracknell's paper is excellent. I highly recommend it because it also talks about how there is overlap between those pixels. So they're not just sampling what's inside a 30 by 30 meter space. It's actually an ellipsoid area on the ground, and they overlap on purpose to capture all the data. And then there's actually, this is the function that they found for AVHRR remotely sensed data. This is the sampling that occurred. So the values in your remote sense data are going to be better representative of those at the center of the pixel than the edges, which kind of makes sense, but it also means we could miss things. When you resample data, you're also going to introduce error. In other words, if you reproject or you do anything that changes your rasters in any way, usually it's reprojection, or resampling, you're going to get different pixels. In other words, this pixel, if you use bilinear interpolation, is going to be an estimation based on these 4 surrounding pixels. So this pixel is going to be very close in value to this one, but these are going to have some impact on it. So again, we're sampling one raster to get another one, so there's going to be error in there. Not as much, but still some. So the basic approach here is to estimate the standard deviation of the original scene that the pixels represent, and then use that estimate to create predictor rasters that we downsample for modeling. And we can then inject error into them as well. Okay, so here's original raster 10 meters. Here's the original raster with some noise injected into it. Okay, doesn't look very different, except you can kind of see it has this texture to it. So that's a covariate with noise injected. Again, we create the model with a mean raster. We inject normally distributed random errors into the predictors, and then we recreate the model, do this over and over again, saving the results. And then from those results, we can create a distribution of the parameters and performance measures. In other words, each time through here when we create the model, we get our performance metrics, R squared, AIC, AUC, whatever you're using, stick those in an array, and then when we're done looping, we can then say, oh, here's our mean AIC and our standard deviation of our AIC based on the amount of noise that we've injected into our model. Cool methods. Okay, now remember that many of our predictors are interpolated. There's a little bit of a problem with that. If they're done with kriging, it provides a standard deviation raster as one of its outputs. But usually those aren't available. You can create those in ArcGIS, but I don't know I've ever seen one supplied with a Krieg layer. If we had the point data and we could recreate the interpolated surface, in other words, if we were doing the interpolation ourselves, then we could inject error into the point data, do the interpolation over and over again, and we could characterize the amount of error that's there. So there's different methods we could use there. We're not going to do that in this class, but you could. I just want to make you aware of it because it could have a big impact. We saw this when we were working at Escalante National Monument, the largest national monument in the country. There are 3 weather stations, all at airports, and they're on the border of the national monument. They're not even in the interior of it. So if you've ever been to that area of the Southwest, it looks like this, right? It's all hot and dry. It's all the same. Well, except for places like this. So there's these incredible canyons where suddenly you go from dry, hot, arid environments into much more humid and wet environments. And here's a picture of Zion. You can see the same thing going on here. Now, why is that a problem? Well, the data was collected at airports, flat spots near roads, and it's just not representative of the whole landscape. So in other words, if you have a weather station here on a flat spot and here on a flat spot, and in between you've got a canyon, when you interpolate across that, you're going to completely miss this canyon. And we saw this when we were modeling or trying to model Tamarisk in Escalante National Monument. Now the data sets like PRISM take into account topography and they try and account for some of this, but there's still going to be a big impact from this. It's still going to miss the canyon and the characteristics of it. So again, if you create an interpolated surface, use Monte Carlo methods to do it over and over again with different data sets, different sets of points, validation approach, and definitely include the extreme points if you can. Often you won't be able to, you simply won't have data from them. And then you can estimate the variability that was missed. And you could then use that as a predictor layer, and that would give you an uncertainty raster. Anyway, we'll talk more about this in the lab.